these curious discussions that you have that I think to the lay person it's a little bit boring. You know, as I'm currently in the midst of writing a textbook, and one of the things that I find that you don't realize at first when you decide to do that is that there are things that you write that are really, really fun to write about. You can't wait to get to that section where you talk about that really important thing. The trouble is there are other sections that you do not care about at all, but they have to be there. There are things that are absolutely essential to, you know, knowledge and understanding of these things, and you sort of have to power through them. Today is just such a discussion. It is mathematical and eminently practical. It'll involve some mathematical skills which might be slightly unfamiliar to you today, which will be coldly understood by the end of the course. But I want to warn you, alert you to the fact that in today's discussion there is something extraordinarily deep going on. And I'm going to try to allude to that a little bit as I go along in the hopes that throughout the course I'll begin to shade that in a bit more, and you'll have some, at the end, some subtle knowledge that you might not even be aware of. But as I've been going along defining displacement, velocity, and acceleration, I have mentioned in passing their nature as vectors, vector quantities. A vector quantity is a new kind of quantity that you hadn't heard of before until you started doing physics. Of course, there are all kinds of numbers in mathematics, real numbers, imaginary numbers, quaternions, all kinds of strange things that math folks have come up with. But the vector quantity is just a new kind of number that has a very specific definition. In the future, like far in the future, but beyond this course, you may discover that the definition that we'll choose to use for this course is a little bit inadequate. But for now, suffice to say that there are some quantities that have both a magnitude, an amount, and a direction. Such quantities are vectors. The easiest vector to think about is the velocity, because I could be going along at 5 meters per second that way. That way is a very specific direction. This is one way in which velocity is distinct from speed. From time to time, someone will carelessly say that velocity is speed with direction. Of course, we know that's not true, because part of the definition of velocity is that it is the displacement divided by time, whereas speed is the distance divided by time. The distance and the displacement don't have the same magnitude necessarily. There are occasions where speed and velocity have the same magnitude, but it's not always true. So you have to be careful about that subtlety. But as I've said a couple of times already, I know, velocity is the more useful quantity to physics anyway. So anytime I say speed, I'm just being sort of casual with the language. I really most likely mean velocity. So velocity is a vector quantity. It has an amount, which I'm not so much concerned about today, but also a direction. And the most convenient way to describe that is to draw an arrow, say a velocity v like this. And those of us who have some practice, I'll draw an arrow that sort of goes off in a random direction and call that a velocity v. And some of us who have done a bit of physics before, solved some projectile motion problems, in fact, all of us have done that in preparation for this course, know that something that you would like to do with this velocity vector is to resolve it into its components in some coordinate system. Now, the coordinate system I most often choose to solve physics problem, of course, is x and y, right? And that's where I sort of went off on a tangent and talked a bit about coordinate systems and what they mean and how we choose. There are many coordinate systems. So far as I know, and maybe my experience is imperfect here, there's about 11 coordinate systems that are useful, right? And you can probably name Cartesian coordinates, right? Polar coordinates, what we call cylindrical or azimuthal coordinates, spherical coordinates, you might have gotten that far. But there are others. There are elliptical coordinates, hyperbolic coordinates, there are Jacobian coordinates, all kinds of fancy coordinate systems that have been made for the convenience of certain problems. So for today, I'm just going to imagine that my convenience is to solve problems in the x and y plane. And naturally, my tradition is to set the x-axis to be the horizontal axis and positive to the right. That is arbitrary, completely arbitrary. I can manipulate it anywhere that I like. All that matters is that I make this declaration. But let's imagine that the x-axis is along this way, and maybe I'm going to just make it up with my diagram. I'll draw a dotted line here to indicate to me that that's the direction of the x-axis as it's traditionally drawn. I drew it way too far, so I'm going to shorten it up a little bit. Sometimes you'll see me make adjustments to diagrams for the aesthetic. If your diagram doesn't look like mine, that's okay. Although I have a suspicion that being obsessed with the aesthetics of these things might be part of success in it. I'm not sure. So once I cast this vector, velocity vector v, into the coordinate system, there's a thing that I want to be sort of clear about here. I have placed the tail of my vector, that is the non-pointy end of the vector, I've placed it at the origin of the coordinate system. It does not have to be there. Any vector quantity, like this velocity, can be plucked off the board and carried around, moved around from here to here, and because all I have to do to keep that vector the same quantity is to maintain its magnitude, that is, don't make it any longer or any shorter, and don't change its orientation in the coordinate system, that is, don't change the direction that I'm pointing. It doesn't matter where it sits. The reason why this is an important point to make is that you can, when you're working on a problem and you have some vectors laying around and whatnot, perhaps in your diagram that you've drawn, you can move vectors around if conceptually it helps you understand the nature of the math that you're trying to do. But at any rate, we know, those of us who have solved a bunch of projectile motion problems know, that a convenient thing to do here is to realize that this velocity vector v can really be described as two parts, so-called components of the velocity. A part of the velocity that is directed along the x-axis, which I'll draw in here and give it a very sensible name called vx, and a point that is directed along the y-axis, or a part that is directed along the y-axis called vy. This is decomposing the vector in its components, and because of the nature of right triangles, it's very easy for me to define what these components are equal to. Obviously, Vx, since it is adjacent to the angle, is going to be the cosine component, so it's simply V times the cosine of the angle. And Vy is therefore the opposite side, and I know related according to trigonometry, this is the sine of the angle, Vy sine theta. And so I have those components, and I know that if I should have the components Vx and Vy, there's a simple relationship that gets me the velocity vector back again, and that is that the velocity vector V is equal to the square root of the sum of the squares, the so-called sum in quadrature, Vx squared plus Vy squared, square root. And then I could reformulate the angle by using the inverse tangent of Vy divided by Vx. And these are all very obvious statements about the behavior of vector quantities that is going to be formalized by a new kind of notation that we haven't seen before, but is prevalent in physics. And that is the unit vector notation. So I'm going to move away from velocity vector, my comfort zone here, where I'm talking about a quantity that's very familiar as a vector, and instead talk about an arbitrary vector A in a coordinate system. And you're going to find it's drawing a very similar diagram. This is the vector A. I don't know what its physical significance is. I'm just saying it's some vector A could represent any vector quantity. And I want to write it in terms of two components. Well, in order to do that, I'm going to define vector addition. Because once I have vector quantities, the very next thing that I'm going to do is add, subtract, multiply, and in principle divide them. It'll turn out there is no vector division, but there are two types of vector multiplication. So I have a bit of work to do. So here's my vector A, and I'm going to define another vector B, and I want to examine what does it mean, or actually not examine, I want to define what does it mean if I take vector A and I add to it vector B. That is, what is the definition of vector addition? It's critical here that I say the definition of, because this is not derived fundamentally from any other principle. This is from scratch. I just say that it is this because I say so. Well, that's a little bit strange. Why can I just make things up arbitrarily? Well, it turns out that they have utility. And the utility comes in a moment after I have this definition. But what I'm going to say is that the way that I add vectors, or like the concept of adding vectors, is that I take the vector A, which here I'm going to draw again. There's my vector A. And in order to draw the vector A again, it's quite challenging on the board. I have to draw the vector of the same length and in the same direction that I drew it the first time. And then I'm going to draw the vector B, except I'm going to pick B up off the board and move it over so that the tail of B is at the tip of A, and draw it this way. And I mentioned that I can go ahead and do that as long as I keep the magnitude of the vector and the direction of the vector the same. In your own diagram, you should try to keep those two of the same length and the same direction. So now what I'm going to say, I have the vector B here, tip to tail with A, and I'm going to say that the definition of vector A plus vector B is the vector drawn from the tail of the first to the tip of the last. That is, I start here at the tail of vector A, and I draw a vector that points to the tip of the vector B, and that is going to be a vector C, where I state that by definition C is equal to A plus B according to this diagram. I've used 3 tick marks there on my equal sign to mean, oh, really equal to by definition to, by definition of. It's equal because I say so, which is pretty great. You don't often get to do that. If we could do it all the time, everything would be much easier. So C is equal to the vector A plus the vector B. That's what I mean by vector addition. So when I have any 2 vectors, I can add them up to make a third. And indeed, if I have multiple vectors, 3 vectors, I simply proceed with them tip to tail, tip to tail, tip to tail, from the tail of the first to the tip of the last. And that is the definition of vector addition. Every once in a while in our physics, we encounter vector subtraction. And it's a little bit useful to us in our physics and in our exams to understand how that works graphically. It's a little bit strange. Vector addition, quite easy from the tail of the first to the tip of the last. What do I mean when I do vector subtraction? Consider the same vectors A and B, and I've written this relationship that that C is equal to A plus B. Well, I can do some subtraction here. I can manipulate this algebraically the same way I would with ordinary real numbers. And if these were just x's or y's, that's some sort of algebraic equation, I can perform that algebra here so that I can say that C minus B is in fact equal to A. C minus B is equal to A. So the graphical interpretation of this is that if I want to subtract 2 vectors, and while C and B are subtracted here, it seems to be that if they're tip to tip, you draw from the tail of the first to the tail of the last. But I can also rearrange this in another way. In principle, I suppose the way I should have done it first, sort of regret the algebra that I did because of the way I drew the vectors. But I can also write that C minus A is equal to B. So I have C minus A is equal to B. And this is the interesting one to me, because what I've done with C and A apparently is I've put them tail to tail. And then the difference between C and A, the difference between those 2 vectors, is a vector drawn from the tip of the second to the tip of the first. And that is the difference. The reason why this matters to me is a very specific instance in our physics that we've already been studying as we warm up for this. I'm going to go back for a moment to the context of velocity. Consider that an object is moving along with some velocity v. So I'll call it v0. That's a very sensible thing, an initial velocity. But then that velocity vector changes direction a bit. It changes direction a bit to a final velocity vector v. Now I'm going to deliberately draw them tail to tail, because it turns out, and I'll show you algebraically, it's quite simple. If this is the velocity vector v0 and it changes to v, you see the magnitude hasn't changed much, but it's changed in direction. It's like it's turned a bit. The velocity vector has turned. I could have changed the magnitude as well. I chose not to do it because it's a very specific instance that I have in mind, but it's turned a little bit. What is this vector that points from the tip of v0 to the tip of v? Well, it turns out it's delta v. It's the change in velocity vector that points from the initial velocity to the final velocity. Now, delta v, I already know by definition, any delta v is the final velocity minus the initial velocity. That's how I define that. That's how I define the change in that quantity. Well, look at the algebraic manipulation I do. If I add v0 to the other side, then I get delta v plus v0 is equal to v, all vectors. But this vector addition, it doesn't matter what order I do vector addition, because it follows all those usual algebraic rules. It doesn't matter what order I do the vector addition in, so let me reverse it so that v0 plus delta v is equal to v. Well, look what's happened. If I look at my diagram, v0 plus delta v is equal to v. So returning to my vector addition scheme here, where in order to add 2 vectors, I put them tip to tail and draw a vector from the tail of the first to the tip of the last. That's what happens. This expression, in the context of this diagram, v0 tip to tail with the change in velocity is equal to the velocity. The reason why I mention this is that it will be useful to you at some point to look at a set of vectors and sort of imagine which direction the difference vector points. This vector, delta v, points in a very specific direction here. This vector, delta v, is used to define acceleration. That vector, delta v, is the direction of the acceleration. So understanding the relationship of vectors when it comes to vector addition and vector subtraction is kind of a little bit, it's a little bit of utility to you to be able to do that. That delta v is going to point in the same direction as the acceleration vector on average. Of course, it's a delta quantity, not a dv, and so it's only an average value according to that. So, vector addition and vector subtraction. What I'm going to do is draw again my vector A, and now just so you know what I'm up to, because I don't know what I'm up to, I'm pretty much making this stuff up. I'm going to describe my generic vector A as the sum of two vectors in component form. That is, I realized, just as I did over here with my velocity vector, and a formulation is very familiar to me and when I'm going about solving problems, particularly projectile motion problems, that this vector A can be written as a component directed along the x-axis, which I might call AX, and a component directed along the y-axis, which I might call AY. The unit vector notation, which is the whole purpose of this discussion actually, is to get into the unit vector notation and describe it. The unit vector notation comes about by realizing that the vector A could be written as the sum of two vectors, a vector whose magnitude is AX plus a vector whose magnitude is AY. And when you look at this diagram to start off with, you might not immediately see vector addition there. But remember, I can place vectors anywhere that I want. So I grab hold of this vector that points vertically, AY. It's not really a vector, but AY that points, it is a vector. I grab hold of this vector and slide it over here so that AY is placed in this location, AY. And you see now I have a diagram that reminds me of my definition, my graphical sort of definition over here of vector addition. That if I place two vectors, AX and AY, tip to tail, then the sum of those two vectors is from the tail of the first to the tip of the last. So I suppose I should have harpoons here. Let's go ahead and add them. AX and AY have harpoons there. It's the sum of two vectors. So the vector A is written as the sum of two vectors, and that is not terribly convenient, because A has its own set of vectors, AX and AY. This doesn't apply to every vector everywhere. It just applies to this one vector that I made up. Well, now, two definitions. I'm going to define a brand new vector called I hat. It's an I with a little triangular hat on the top of it instead of a dot. I hat is a very special vector that I invent. This vector I hat is equal to, or sorry, I should say, I'm going to describe it graphically here first. I hat is a vector that points along the x-axis right here. It's a vector that by definition points along the x-axis. You might wonder, why not call it x hat? I wouldn't be surprised if somewhere there's a textbook where they call it x hat. There are also books where it's called E sub x and all kinds of other funny ways of describing it, notation-wise. But the most conventional notation, and certainly the engineering notation, and certainly the American notation, is I hat. I hat has another property, special property though, than the fact that it just points along the x-axis. It has a length of 1. It has a length of 1. And so the vector that points along the x-axis divided by its own magnitude, I guess I had a way I wanted to write that, but I can't conceive of it at this point. But I guess I'll say here the magnitude of I hat, that is the length of the I hat vector, is just 1. The utility of this, and this is I mentioned that there was a bit of subtlety to it. Here comes the subtlety. Like if we pay careful attention to this and we internalize this, a lot of things about our universe are going to suddenly become very clear. The utility of this is that any vector that points along the x-axis can be written as a multiple of I hat. For example, the vector that I call AX can be written as the amount AX. Notice the harpoon has vanished. Just the amount of AX multiplied by I hat. Because the effect of multiplying a vector by a scalar is that you just multiply the magnitude when you multiply a vector by a number. But the magnitude of the unit vector I hat, the name makes sense, right? Unit vector, 1, unity. The magnitude of the unit vector is 1. So when I multiply it by AX, I get a vector AX, long, that points along the x-axis. So the vector AX can be written as a multiple of I hat. Similarly, I define a vector that points along the y-axis that I call j hat. Again, the magnitude of j hat is certainly equal to 1, so that I can write a vector component ay, which I've drawn on my diagram there, as ay multiplied by j hat. We're going to do some things in 3 dimensions. We can't help it because particularly in second semester, some of our physical laws will be 3-dimensional. You can't stay in 2 dimensions. You can do projectile motion in 2 dimensions all day long because projectile motion is a 2-dimensional phenomena unless you include the rotation of the Earth in which things turn, right? Like hurricanes. But I need another axis, so along the z-axis, which I don't have on my diagram, please pardon me, is k hat. A unit vector called k hat points along the x-axis, has a magnitude of 1. So in principle, if my vector A was 3-dimensional, I could have a component of it, az, which was simply the magnitude az multiplied by k hat. As you look at this, you might be thinking, my God, this is a waste of time. It is difficult to spot the utility in it until you've used it a lot. And if you're like me, you'll never really enjoy using it, but it is the way to go. So let me rewrite. Originally here I wrote the vector A as the sum of 2 vectors. That is, A is the sum of its components. And we knew that. But now we write it in the unit vector notation where I write it as AX I hat plus AY J hat. And then in principle, if you like, plus AZ K hat, if it happened to have a Z component. Now, this is where it gets really fun and interesting. The principle of linear superposition. The principle of linear superposition applies in more ways than you've imagined to this point. What I'm saying here is that any vector in 3-dimensional space can be written as the sum of I hat, j hat, and k hat if I choose the multipliers properly. All I have to do is choose the components properly, and then I get a mixing of I hat, j hat, and k hat that creates the vector. There's all kinds of beautiful math language here that's fun. The reason why we can do this is because I hat, j hat, and k hat are linearly independent. What a fancy term, linear independence. You're going to hear it more in your technical subjects. What a fancy term, linearly independent. Why are they linearly independent? Because you can do this. It's linear. What, I don't get, how's it linear? Ready? I guess what I want to say here, what I want to open your mind up to so you can like really be good at stuff, is to realize that things are way more the same than they are different. Way more the same. Symmetry. This vector thing is the same thing as lines. Do you remember how much time you spent in math class learning about lines, y equals mx plus b? Y equals mx plus b? I'm going to change that. I'm going to change it in a way that they should have done when they taught it to you, except that it would have blown your mind and you would have been like, why is this happening? Let me write my vector here. I'm trying to do this in a stylish way to make the lecture more fun. A is equal to ax I hat plus a y j hat. Yeah? Yeah? Now, think about your point slope form y equals mx plus b you learned in math class. Any line in the xy plane can be written as a linear superposition of 2 components, x to the first and x to the 0. It's the same thing. Do you see how different those 2 things look? It looks like something. It's the same thing. It's exactly the same thing. And x to the 0 and x to the 1. Of course, x to the 0 is 1, right? But x to the 0 and x to the 1 have a similar property to I hat and j hat. There's nothing remotely I hat about j hat. They are perpendicular to each other. 90 degrees between them, right? There is nothing over here like the y-axis describes. Only the up and downy stuff, not the side to sidey stuff. There's nothing remote, and some of you saw me write, who read the stuff that I write, saw me write a blurb where I say like a funny little thing. There's nothing remotely sideways about up. They are linearly independent. Let me hit you with another fun word. They are orthogonal, right? See, I hat and j hat are linearly independent. Sure, they're linearly independent because that angle is 90 degrees. Of course, I hat and J hat have nothing to do with each other. They're perpendicular. They have nothing to do with each other because they're perpendicular. See, but it's not about perpendicularity. That's why I have the word orthogonal, because the monomials, x to the 0, x to the first, x to the second, x to the third, x to the fourth, are orthogonal. And by the way, you've certainly realized when I made this linear claim, any parabola can be written as a linear superposition of x to the 0, x to the first, and x squared. You just have to get the coefficients right, do you see? And so any vector can be represented this way. This happens all over the place. Let me hit you with another linear superposition that you're familiar with, RGB. Any color can be made of a linear superposition of those. Any color can be made. All you have to do is choose the coefficients, and the coefficients are the intensity of the color. And then any color can be made. It's the same thing. It's exactly the same thing. You say, well, Charlie, I don't like I hat, J hat, K hat. I'm gonna invent my own. Feel free, because what is it? Cyan, magenta. There are other schemes. Cyan, magenta. What are they? There's yellow. Cyan, magenta, and yellow, right? Yeah, we're not artists here. Right. Well, they make any color out of combining those inks, right? By combining those inks with different intensities, they get whatever color. Cyan, magenta, and yellow, they can do that. Linear superposition. Are you ready? Are you ready? Brace yourself. I don't want to talk about this in detail today. I want to talk about this later on, but I'm going to mention it. Ready? Your universe is just about to expand quite rapidly. And when that happens, the air generally rarefies, so prepare to catch your breath. Did you ever hear about the Schrodinger's kitty cat in the box? Schrodinger's cat. Schrodinger's cat is an argument that's made to describe the nature of the quantum mechanical theory. But I have a cat in a box. Inside the box, I place a radioactive sample that radioactively decays according to a random process. I don't know when it's going to decay, but I know that it will. And then I have a little radiation detector there that's attached to a spring-loaded mechanism that hits a vial of poison that kills cats like nobody's business. So I put the cat inside the box, and I close the lid, and then I stand back and have the discussion. Is the cat alive or dead? This is where these things are going through your mind right now. Well, you just listened for the sounds of cat choking. I'm going to say this one more time. It's not a real cat. It's actually a two-level quantum mechanical system, right? The little electron oscillating between two potential states. So something happening inside of an atom. But we can't have that discussion because the behavior of electrons inside of atoms is nothing that we've ever seen. We don't have any experience with electrons inside of atoms. So we have to talk about this damn cat in the box. So if you would, please. Is the cat alive or dead? That's true, but I'm not going to do a whole quantum thing right now. You're going to get the full-on cat in a box later. I promise you. Full-on cat in the box later. But for now, what we've come to realize, and this is the amazing part, the cat's existence is a linear superposition of alive and dead. There are two ways for the cat to be, alive and dead. The way the cat is a linear superposition of alive and dead. So I could write it like this. That's some crazy notation I never saw before. Yeah, but it's just notation. Notation has to be agreed upon that we understand what it is that we're talking about. That weird looking thing, which is called a ket, by the way, with a cat inside of it. It's a cat and a ket. This says cat is a sum of alive and dead with appropriately chosen coefficients. Y is equal to x to the first plus x to the 0 with appropriately chosen coefficients. The vector A is a vector sum of I hat and J hat with appropriately chosen coefficients. This is the principle of linearity, linear superposition, and it pervades all of our science and engineering, and we don't even see it happening. And there's a huge advantage to the person who can see it happening. When you see linearity and what's going on, you'll be like, well, it's just a linear system. And then all of a sudden, all those matrices that they tried to teach you, and you're like, matrices? What are these even for, man? I don't get it. Oh, matrices. Our good friend Werner Heisenberg created an entire formulation of quantum mechanics that was all matrices from one end to the other. Beautiful, 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 beautiful. And I'm going to teach you some of that stuff. As a matter of fact, in our course with our physics, I'm going to teach you some matrix techniques, because in an electrical circuit, the relationship between the voltages and the currents is extremely complicated, but completely linear. And I'll take advantage of this in solving those kinds of problems. So, linearity. A place where you have seen linearity intersect with your physics problems is if any of you have ever done a Newton's law thing, where I examine a physical system and there are a number of forces which act. And I've said that the total force that acts on a system is the sum of all of the forces. That sum is a vector sum, and vector sums are linear, and so that is a linear system. Right? I'm starting to get used to the fact that linear systems are all around me. There's another kind of physical system, which we will not learn about in our physics, but I'm seriously considering creating a physics after party thing related to it. Not all physics is linear. Not all physics is linear. You can imagine when it goes nonlinear. Wait a second, that sounds familiar, doesn't it? Nonlinear dynamics. Have you ever heard that before? All right, when we study forces in our physics and the way it affects motion, that's called dynamics. There is an entire branch of physics called nonlinear dynamics that you've heard of before, but you just haven't heard it called nonlinear dynamics. Does anybody know what I'm talking about? Chaos. What is sometimes called chaos theory. I'm not wild about the term chaos theory because in my imagining, if it's a theory, then it's not really a problem. It's not really chaos, is it? It's not really chaos if there's a chaos theory. And it turns out there are still mysteries to nonlinear systems. And don't even get me started on quantum nonlinearity. It's crazy. Right? Linear systems analysis, really, really good stuff. And there's linearity to vector notation. So I know for a fact that even though I've given you these subtleties and I've talked about it, you're still going to hate the component form. Sorry. Particularly in our computer system, when you're entering in answers, you'll enter in an answer and you're like, but I'm right. I'm totally right. And they bring it to me, Shadi, I'm right. And I'll look at it and go, yeah, you are right. And neither one of us noticed that it's in boldface. And so it expects your answer to be a vector. And so you have to add a k hat or an I hat or a j hat to the end of your answer. You're perfectly right, but you have to have that vector notation there. It can be frustrating. And when you encounter a problem that requires that you use the vector notation, it can be tedious from a mathematical standpoint. It is admittedly not the most fun. Now, I'm going to do all of the vector arithmetic that I know, but I'm going to do it in component form because I know that I certainly will have occasion to add vectors. Because the principle of superposition applies to vector forces and vector fields all through our physics. And so I'll have much cause to add vectors. So I'm just going to go ahead and plow along through this vector addition. But I'm also going to get to two forms of vector multiplication. And we won't really apply those until a bit later in the course. So there'll be a delay between when I'm showing you this now and when we do it later. But what I'm doing is I'm buying myself the right to later on to say, I showed you how to do that. And you'll say, oh, but I forget. Because if you don't use a skill, it'll sort of fade on you. So beginning with vector addition, I want to write a title on here that says vector addition. I'm not going to waste my time doing that. I'm simply going to add two vectors. So here I have my friend vector A, an arbitrary vector that doesn't have any physical meaning, but I could easily imagine it's one of the vectors I'm familiar with like a velocity or an acceleration or even a displacement, some force or something like that. And it has components associated with it, and here I am writing it in the component form. There is another vector B that I would like to write, simply a different vector. So I'm going to add these vectors together. I got a vector A, and now a vector B, if I can write it appropriately. Here's a vector B, and it has components that I'll write differently, bx I hat plus by j hat. And so I know what my graphical definition of vector addition is. I put the vectors tail to tail, or tip to tail, and I draw a vector from the tail of the first to the tip of the last. But it turns out that the vector notation and the principle of linear superposition means that I can simply add these two. By the way, you probably had math homework at some point where you took the equation of two lines and added those lines together. You simply line them up like that, add vertically, and then you get the sum of those two things. Well, here I get a vector C, which is the sum of the two, and I have to be a little bit compact with my notation, but it's simply ax plus bx I hat plus ay plus by. Now I'm like all paranoid, j hat, right? So the lesson here is that in order to add vectors, you simply add the components of the vectors. It's very, very simple. So the I hat component comes from adding all of the I hat components. The j hat component comes from adding all the j hat components. So if I have two vector quantities like forces, for example, and two forces act, I can write them in their component form and add them in component form. From time to time, this happens to us in our physics. I'm not wild about it. It always bums me out. But from time to time, and as a matter of fact, I promise you, when I choose the homework assignments, I try to avoid this kind of nonsense in the homework because adding vectors in component form is just boring, right? So there it is, a vector sum in component form. If I had it in 3 dimensions and there was a k-hat component on, I would typically add that as well, so there's no information there. Now, vector subtraction is going to work exactly the same way, except I'll subtract the components instead of adding them. So it's very trivial. I don't need to say anything about that. What I'm interested in right now is 2 forms of vector multiplication. The first is called the scalar product. It's called the scalar product because it's going to be a definition of multiplying 2 vectors where the result is a scalar. Multiplying 2 vectors where the result is a scalar. This is sometimes referred to as the dot product, which we'll see in just a moment here. Consider that I'm using my same vectors a and b. The scalar product is defined in the following way, that the vector a in product with, using a dot, the vector b is equal to the magnitude of a times the magnitude of b times the cosine of the angle between them. The magnitude of the vector a times the magnitude of the vector b times the cosine of the angle between them, which by the time we get to the end of this course will be very, very obvious to everyone. And for some of you who have already done a bit of physics, I want to point out to you a thing, what this looks like graphically. If I have the vector a and the vector a happens to look like this, and I have the vector b and the vector b happens to look like this, when I refer to the angle between a and b, I naturally mean this angle. Well, look at what this mathematical process does, and you'll see why the scalar product is defined the way that it is, because it's useful. The magnitude of a times the magnitude of b times the cosine of the angle between them. Imagine you shift this around a little bit, and you move the b out, and you move the a in, so a cosine theta. A cosine theta is the component of a in the direction of b. Now, I've drawn b as if it's along the x-axis. It doesn't have to be. What the scalar product does is it takes the projection of the first vector in the direction of the second vector, no matter what its vector is, no matter what its direction is. This is called vector projection. In a sense, it's finding the component of A that points in the direction of B. Some of you would wax nostalgic about this because you realize that when a force does work on an object, only the component of force in the direction of the displacement does work, which makes the scalar product a very handy thing. If that means nothing to you at this point, don't worry, because we absolutely will come back to this. But in describing or giving this definition of the scalar product, I haven't used the component notation. I can write the scalar product as well in component notation. Here we go. A dot B in component notation, imagining that I know A and B defined this way, is very, very simple to do. You have A and B defined in terms of I hat, J hat, K hat components. What you do is you multiply the components, AX, BX, for example, and you add to that AY, BY, and you add to that AZ, BZ. Notice that these are just the coefficients of the I hat, J hat, and K hat. They're just numbers. So I'm multiplying the components and adding them through. The result, of course, is a scalar, just a number. It has no vector quality to it whatsoever. The vector A dotted into the vector B, this is the scalar product. But there are 2 kinds of vector products. Well, 2 kinds of products among vectors. The second is called the vector product. And that is a very, very sensible name to give it because whereas the scalar product has a result that is just a number, the vector product has a result that is in fact a vector. It has a shorthand name though. The vector product is often referred to as the cross product. The vector product is often referred to as the cross product. No. Subtraction, well, yeah, they're tail to tail. I'm setting it up that way. But of course the subtraction would be from the tip of A to the tip of B, and that's not what I'm doing here. Yeah. The vector, it looks like it says gross. The vector, the so-called cross product, has a result that's a vector. Now you won't be surprised to see me write it like this. A cross B, you see how we get the difference between the 2 products there, A with a cross, B, is equal to, you have to be careful now, the magnitude of A times the magnitude of B times the sine of the angle between them. That can't be the definition. Can't be. Because the result of that is not a vector. The result of that is a scalar as well. So what I have to point out here, a difference between this line and this line, is that I put magnitude symbols on this. The magnitude of the cross product is calculated that way. The magnitude of the cross product. Now, the next thing that I did here, imagine again my vectors A and B. What I want to do is see if I have any physical interpretation. Well, that's a little radical. Here we go. There's vector A, there's vector B again, pointing in this direction. There's an angle between them, theta. How do I interpret this? We're over here with the scalar product. It was the component of A in the direction of B and then multiply. That's cute. The magnitude of the cross product is the area of this parallelogram. What does that mean? I don't know. Very strange. Very strange. It's the area of the parallelogram. How am I supposed to interpret that meaning? So I have to calculate now the vector cross product in its component form. The way that I'm going to do that is by using a mathematical mnemonic. It's not really a math procedure. It just looks like a math procedure. And it's the way that everyone who has need of doing a cross product actually gets a cross product done. It's going to look a little bit mysterious, so I don't blame you if the next time you have to do it, because it will come up that you'll have to perform this procedure. Not all the time, but once in a great moon you have to do it. If you have to go look it up again, because it's somewhat difficult to internalize. So let's say I have my vectors A and B again, where it's A cross B is the vector cross product that I want to compute. Well, A cross B is going to be found by creating this matrix, which along its top row has I hat, J hat, and K hat. And that's really the strange bit about it, is making a matrix that has elements that are in fact the unit vectors. And along the next row, I'll have the components of A, which I know to be AX, AY, and AZ. And then the very last row here, I'll have the components of B, BX, BY, and BZ. And then I'll put a bar on the other side here, because what I'm going to do to this matrix is take the determinant. Again, not a mathematical thing I'm doing, but a mnemonic thing, because I reach a point in my study of mathematics where I know how to take a determinant of a 3x3 matrix. The technique of finding the determinant of this matrix is what's known as expansion by cofactors. Because I know how to take the determinant of a 2x2 matrix, and I can use that as a trick to take the determinant of this 3x3 matrix. So the very first thing I'm going to do in this is I'm going to find the I hat component. And the way that I do is, in my mind, I'm going to sort of use my imagination to cross out the top row and the ith column. And when I cross out the ith column and the ith row, I have this 4x4 matrix here that I know how to take the determinant of. And taking the determinant is simply multiplying the diagonal elements and subtracting. That is, it's AY, BZ minus AZ, BY. And if you've never taken a determinant before, that's an extraordinarily mysterious thing to do. But it is, as I say, later on in math, is a pretty standard practice. So that gets me my I hat component. And now to get the J hat component, I have to remember. Remember, this is just a mnemonic I'm doing here. I have to memorize the fact that I should always put a negative sign for the J hat component. I always put a negative sign for the J hat component. It always has to be there. So then what I'm going to do is cross out now the jth column and the top row. It's a little bit trickier because when I cancel out the jth column, I've eliminated the AY and BY elements, and now I have a 2x2 matrix that is AXBZ, AZBX. And so that's going to be my J hat component of this, AX times BZ minus AZ times BX. And you see, I'm looking back to my matrix here because, in fact, I do not have this memorized. I need this mnemonic in order to work this out. So I continue on that way. So that gets me my J hat component. You would not be surprised with the K hat component, which is just plus. There's no negative sign associated with that one. For the J hat component, I'm going to cross out the jth column in the top row. And that leaves me with AX, BX, AY, BY over here for that. And so I'm going to take the determinant of that submatrix there, AX BY minus AY BX. So here I have a vector result. Now remember, if I well, I don't define, but if I write my cross product as the magnitude of A times the magnitude of B times the sine of the angle between them, the result of that is a scalar. But this is the vector product. The result is in fact a vector. So this is the true definition of the vector product, and it gives me a vector. At this point, it's hard to determine, like, what is this going to be useful for? But it'll turn out that some of our physical laws, our more sophisticated physical laws, particularly in the second half of the course, are going to have cross products in them because they'll be vector laws. And so there'll be a cross product inside the law itself. So this is going to be critically important. But it is a vector. And so it has a magnitude, which is easily computed as the sum and quadrature of all of its components. But what is its direction? Well, this is where we encounter a thing that I've already alluded to a bit when it comes to coordinate systems, the right-hand rule. Let me show you something curious you may have noticed when looking at this vector cross product. Do you see that the I hat component depends only on y and z components of the vector? And the j hat component depends only on x and z. And the k hat, which is the z-axis, depends only on x and y. That is, I don't know how to say it. There is mixing of the components. But the x-axis component does not depend on x components, and the y-axis component does not depend on y components, and the z-axis component does not depend on z components. A consequence of this, which you can enjoy proving, is that if A and B are the two vectors that I do a vector cross, the result of the cross product is perpendicular to both vectors. The vector cross product is perpendicular to both. Now I'm going to make do a little demonstration here with these two pens. Take these two pens and imagine that they're vectors. Of course, they're identical pens, so they happen to be identical vectors. That's not required in any way, shape, or form. Their magnitudes could, in principle, I'll make their magnitudes different. There you go. So magnitudes slightly different. And I'll put them tail to tail. Do you agree with me that any two vectors placed tip to tail, no matter where they are in three-dimensional space, they're flat? There can be a plane defined, right? Any two vectors attached tail to tail defines a plane. The result of the vector cross product is perpendicular to that plane. The result of a vector cross product is perpendicular to both of the vectors which have been crossed. The trouble with that is there are two vectors that are perpendicular to these two. One that points this way and one that points in the opposite direction. That is, if two vectors define a plane, then there are two vectors that are perpendicular to that plane. In a sense, one that points upward and the other points downward, however you want to define that. So the question is, which one did I get out of this? The answer is determined by what is known as the right-hand rule. I have these two vectors A and B, and here they are, as originally drawn, with the vector A and B drawn tip to tail. And obviously these are vectors with two different magnitudes. I want to find the direction of the result of the cross product. Finding the magnitude of the result of the cross product is easy. Magnitude of A, magnitude of B, sine of the angle between them, multiply, boom, I have the magnitude. How now to find the direction? I take my right hand, and this is tricky because some folk accidentally use their left hand, particularly left-handed folk. So left-handed pocket, right hand. I point my fingers in the direction of the first vector in the product, which in this case, since I'm doing A cross B, I point my fingers in the direction of A. I then curl my fingers in the direction of the second vector. My thumb points in the direction of the result of the cross product. So in the case of this arrangement of A and B that I have on the board here, the result of the cross product is directly into the board. A and B lay in the plane of the board. Right-hand rule dictates that the result of the cross product is directed into the board in the direction of the smallest angle, right? So you go the smallest around. And it gets a little bit tricky because some folk want to be like, my fingers don't go that, like how am I supposed to break their hands trying to do the right-hand rule? It's not point your fingers in the direction of A and curl all the way around to and like, you just have to figure out which way they're going because, the trick of the right-hand rule is your fingers don't go both ways. So it only goes the way that, Well, let me flip it by saying, what would the result be if it was B cross A? If it were B cross A that I was trying to compute, then I would point my fingers in the direction of B and curl my fingers in the direction of A, and the result of that cross product would be out of the board. We're going to encounter the right-hand rule again during our course, so it's fitting that we took a moment to talk about it now.